Hey, so my name's Nathan Teder. I'm a PhD student at Adelaide University, and my talk today is focused on research that we recently published entitled Sea Ice-Free Corridors for Large Swell to Reach Antarctic Ice Shelves. First things first, sea ice. So sea ice extent in Antarctica is at its lowest in February and peak September. So this defines our sea ice retreat, sea ice advanced seasons. Image on the right is just the example of what sea ice looks like. And overall, there had been a positive trend in sea ice extent of about 1.6% per decade between 2019 and 2016. This positive trend and extent ended up peaking at 2014. This is despite a negative trend of 2.9% in the Bering Shells at Edmonton Sea. Really, what drove this trend was sea ice growth in the Western Pacific and Indian Ocean sectors. Now, after 2016, there was a sharp decrease in the sea ice extent, and it ended up getting to a record low in 2017. The other factor we're dealing with in our research is swell. So this is another factor we bring in. This is surface gravity waves which are no longer influenced by winds. They are longer than wind waves and will carry larger amplitudes. And with swell in this case, we're in the Southern Ocean. This is the most energetic ocean in the world. In summer, you will get means of about, on average, 4 meters, 5 meters in winter, as the image on the right is a plot from our altimetry data of averages. You can see it is going to be sector-based. For instance, east of the South America, you will see that waves drop off a bit. Around off East Antarctica between Australia and Africa, you can see waves are even a bit more stronger than usual. Now, in terms of between the 1985 and 2018, one thing that was found by Young et al. Was that extreme waves, so significant wave heights of the 90% percentile, had increased by about 0.25% per year in the Southern Ocean. So extreme waves are becoming more common. When combined, this indicates, so the first thing is a loss of sea ice will leave ice shelves exposed to local swells. So why it's so important? And this will then impose flexible strains on ice shelves. So it'll hit it, it'll fatigue it, flex it, potentially remove some ice, and this can lead to riffing and calving events. It can also act as a precondition or potentially trigger ice shelf disintegration around Antarctica. An example of ice shelf disintegrations would be the Larsen B, which is the blue stuff there in the NASA science imagery being what got destroyed. And really, the Larsen B is kind of an example of everything kind of working in conjunction with one another. So, we know swell can create this issue, we know swell is growing, and we know sea ice is variable. However, there isn't a lot done on how, long-term trends and how this has grown and changed over time, and that's really what we tried to answer, was trying to build an algorithm that could answer properties of these sea ice corridors for swell to propagate through and reach Antarctic ice shelves. And when I say corridor in this point, what we just mean is a part of the ocean a wave can propagate through, reach the shelf without deviating or hitting ice or hitting other parts of land. So we want as little movement as possible. Now, first thing when it comes to building an algorithm is what choices are you making with data? And firstly, we decided to grab passive sea ice concentration data sets. So from passive microwave sea ice data set. This is the NSIDC Nimbus 7 SSR. One uses the bootstrap algorithm, been around for a long time. And this data ranges from 1st of January 1979 to now. 25 kilometer square grid resolution, pretty standard for an NSIDC product in the Southern Hemisphere. It does have a 2-day temporal resolution before the 20th of August 1987 and daily afterwards. So I have had to correct that resolution to be daily beforehand. All I've done is just, for all those missing days, I've just taken the before and after and averaged them. So probably the first major question we came to was, what are we going to do about the coastline? It has changed. And we ended up opting for the GFSC 25S landmass. This is a standard with the passive microwave dataset to define the coastline location. However, it is static. It is representative of 1979 bounds. And sea ice shells and extent had decreased at that time. So there is a little bit of systematic error, but we kind of settled on it was pretty unavoidable. And to get ice shelf locations, because that coastline master doesn't give them, we use the measures Antarctic boundaries tool, and pretty much just correlated their lats along with the coastline mask and build a database of locations where ice shelves are. Swell data is the other thing we had to worry about, and we obtained it from the CAWCR Wavepinecast. This is a product from the CSIRO and BOM, freely available, really mainly focused on global oceans and West Pacific, and has been a fantastic product for a long time. Uses the WaveWatch 3 for reanalysis and of observational data. Again, pretty standard. Data ranges conveniently from 1st of January 1979 to now, so it matches nicely with our sea ice data set. For both, we stopped at 2019. 40 kilometers square spatial grid, which is pretty fine for a hindcast, which is great. Hourly frequency, which we have converted up daily. It does have a check and does some filtering on sea ice as well. So it's just something to be aware of moving forwards. And finally, because we are interested in trends, we're interested in changes overall, we had to define years, and because we're interested in something that's probably going to happen in the austral summer, we decided to make our years between September to August to really reflect that sea ice retreat season. How it works, so once we get the model running, what actually occurs, we firstly worry about coastal exposure, which is calculating the length of an ice shelf that is exposed to the ocean. Pretty much really at this point it's saying if it passes this test, corridors can form. Yellow dots are an example in this of the Riesa Larsen ice shelf in 20th of March 1993 of our little schematic. So it's based off, well, it effectively is the Reed and Massam 2022 algorithm they used to calculate coastal exposure. And what it does is a two-stepper. So firstly, it will check all the adjacent cells of a coastal cell and check to see if they're free of sea ice. In this case, we define that as less than or equal to 15%. That is pretty standard with NSIDC products, as the error margin is 15%. Once that's done, it will then just neighborhood check, try and check every cell around it until it either meets or fails an arbitrary area test. In this case, we used 5 million. And this is really just 5 million square kilometers. And this is really just to check if this ocean is actually able to reach the ocean, or it is a part of a polynya, and as we go further out, it will find sea ice. About 5 million, I found, reliably removed every polynya on the coastline, which is why I used it. So the part we really expanded on was actually turning a algorithm that could tell us that there were corridors there to showing that they're calculating what corridors were there. And what we did was, so we took the exposed cell from the coastal exposure, if there was one, picked a cell out on the dataset boundary, calculated a slope, took every cell on that slope, tested it, just ran through it until it either reached the boundary point, if it found sea ice or land. If it did, it would retain the cells that it found previously that had met the exposed condition and discard the rest, and it would just keep going until it exhausted every boundary cell for every exposed cell. So, and once we're done with that, take the union of it, and that is our corridors. We took absolutely everything. If it could reach a coastline point, we wanted it. And A and B, the image of the right, are two examples of corridors. A being the Riesa Larsen that we saw earlier, and that's what it looks like with corridors. It's a pretty simple sea ice setup where the sea ice is only the only player that's an obstacle. The only obstacle is the player, whereas the Larsen B is a more complicated setup where you have land blocking that corridor as the Antarctic Peninsula. You have icebergs that are blocking corridors in certain points, and you have ice where it's actually punching through because it doesn't meet that 15% criteria. And once we did that, we extracted area and duration, corridor outputs, and normalized them, mainly so it makes comparing with other ice shelves easier. Finally, we opted for a 57.5 degrees south cutoff, or the maximum of the sea ice extent, one or the other. 57.5 was a hard cutoff just in case it went further, mainly because the South Georgia islands would occasionally get sea ice, and that would blow it out in summer, and I just wanted to get rid of it. So this is how I end up reconciling it. Once we get to swell data, so once we get a corridor area, the next step is to extract swell data. And the one we were really interested in was significant wave height. This is a proxy for wave energy, and an example of this is from the recent Larsen, our little test bed, and that's what we got. First well does, so you can see up to about 5-6 meters in that day. We also took direction, and we applied a directional field because we put in a pretty big range for corridors at times. We reconciled it by filtering out for directions, preset directions that we said, if it is going in this range, it is going to hit the ice. There's a good chance it's going to hit the ice shelf. We wanted that, and we got rid of everything that there wasn't. It was in the wrong direction. It was going to miss. Like the most energy was going to miss. And then once we got there, we extracted the maximum daily significant wave height for each corridor. And when we looked at individual shelves, so this is mainly, so the image on the right is fraction of corridor days, so duration for gray, and black is maximum corridor area, so per year. And the big thing we kind of found was it was impacted primarily by local features. So another thing to note with the image, so we took 12 prominent ice shelves, and the shaded blue area is anywhere that between summer and autumn for the range of data we had about greater than 80% of days where there would be sea ice there that would fail the algorithm. And when we came to local conditions, that kind of showed it off a bit. So an example would be the Mertz and Cook ice shelf. So the Mertz ice shelf juts out into the ocean and creates an iceberg trap which prevents the Cook from being exposed. Another example would be the Ross ice shelf, which had really low durations because the Ross ice shelf the Ross Sea Polynya would generally close around March. Another example, Larsen Sea. Antarctic Peninsula will protect it from the Antarctic circumpolar current. Weddell Sea grows a lot of sea ice regularly, and that will prevent exposure. So it really did just local conditions really matter. That said though, on average, these durations, these seasons, would be around from late December to mid-April. This is roughly our time where we expect Swell could reach an ice shelf. However, again, individual ice shelves will differ. Range was one thing we looked at, and what we tended to find was it ranged between 0 to at most 208 days. 208 days is an absolute outlier, which is the Wilkins in 2008, and genuinely about anything above 120 days is pretty extreme when it comes to exposure. The other side of the coin, the corridor area normalized. What we found for ice shelves, this tended to range between 0 to 0.6. 0, there's one ice shelf that's never exposed, the land ice shelf. 0.6 is the absolute most. So it kind of indicates on a normal year, even if there is exposure, sea ice is going to stop some swell, some waves from coming in and hitting the ice shelf, or at least attenuate a bit. So there is some loss. Looking towards trends, we use 69 ice shelves to calculate these. So 42 on the east, 27 on the west. The Antarctic Peninsula is included on the west, so Larsen's and Wilkins. And these shelves are all greater than 500 kilometers squared in extent. Top image is normalized area, sum of daily corridor area. Red is when trend line for when these corridors exist. The second image is a normalized ratio variance. So 0 would be mean values, 1 is mean is doubled, -1 mean is halved for the east and west ice shelves, as well as their plus or minus 1 standard deviations. When we looked at seasonal trends, we actually got a little bit of a surprising result here, where duration actually had increased. So despite sea ice extent increasing, and by proxy the amount of sea ice around, our seasons for exposure had also increased. It's by a small positive trend of 0.39 plus or minus 0.37. Normalized area did follow sea ice extent though, and had a negative, like a minor decrease as well, so at least one of them did. And really these trends were underlined by declining area in the east and growth in the west. So the west kind of takes to about 1990, and then as the Bering shells and then moves and sea loses sea ice, you can start to see it really grows with about 3 to 5 times between once you get past 2008, where it is pretty much doubling the mean. The east on the other side, really you can see it starts strong and then just kind of tails off as sea ice grows more, with its last time at doubling mean about before 2000. We're looking at individual shelves, so the top image is looking at the average significant wave height. per day, so climatology over 40 years, irrespective of if corridors formed. And what we kind of saw was, whilst, okay, shelves that had more exposure tend to have like larger swells on average, genuinely, or pretty much early February to late March is really the time where we expect swell to be at its dominance, as much as, again, individual shelves will differ. And when we counted large wave days, so this is our proxy for wave energy and showing what was reaching the shelf, what we ended up finding was we picked 4 shelves of interest out in the east, Fimble, Shackleton, Cook and Totten. Kind of found with this one that, sure, the Fimble was probably dominant just because it was always exposed, or exposed nearly every summer. But generally, if Shackleton was exposed, it would kind of match the Fimble in terms of amount of days. Cook and Totten would pop up every now and then with waves. It's all decently consistent, whereas the West really had a different story. The West, of the shelves we picked, the Wilkins was really dominant. Like, the Wilkins was just ridiculous in this case. Now, the Ross is an interesting one that didn't have a lot of wave energy. It was harmed a bit by the direction filter, though it doesn't really compete with the Wilkins in that sense. But yeah, no, the Wilkins is a ridiculous ice shelf as the TLDR of the second image. And then finally, looking at trends in wave data. So the blue and red bars, the ones that are colored in, are the amount of large wave days per ice shelf in that area. The smaller bars are duration per ice shelf in that area. And what we kind of noticed was there was a regime shift. So what we saw was the West, what we saw was the East really dominating duration, really dominating large wave days compared to the West till the 90s. Then you kind of see both of it correct. So the West doesn't really have the same duration as East per ice shelf. But in terms of wave days, it kind of begins to even up. And then post 2007, 2008, the West kind of begins to really match the East in duration, sometimes exceeding it. And the West, by that, the West also starts to have more wave energy, more large wave days per shelf than the East. Now, this does follow the exposure duration corridor to a degree, though there is a little bit of variance in waves. And one other thing is, what also is likely driving these even higher increases, the West in particular, is the change in the Southern Ocean is also influenced. So, because you're getting less sea ice in that time, the Southern Ocean, we also saw earlier, is becoming more extreme. It probably is playing a role in converting the West's lower durations into higher wave energies. So as a summary of this work, we create an algorithm which will allow us to analyze how frequent ice shelf exposure is and relative wave conditions. Once we looked at the average season for corridors is from late December to mid-April. On average, if we are expecting the large impact from Swell, this will be between early February to late March as our main season of danger, though individual ice shelves will vary. And there was a decline in corridor area in the east, increase in west, and this partly led to larger waves becoming more common for shelves in the west and east compared to its eastern counterpart, though the Southern Ocean does play a role in this. Thank you for listening to my talk. If you want to get in contact, feel free to email me with any questions or any comments, or hit me up on Twitter. Thank you.